Well, hello, retro computing enthusiasts. Mike here. Welcome back to my channel. And today we're going to take a look at my S-100 box here with the Teletek Systemaster in it. It's been a while since I've worked on the S-100 system. The Naboo, my shiny new toy, has been getting a lot of my attention lately, and this has just sort of been sitting around doing nothing. But some of the work I've been doing on the Naboo has inspired me to do new things with the Teletek Systemaster. Now, I have an entire series of videos, and I'll put a link to the playlist for the Teletek Systemaster in the upper right. I have an entire series of videos on this single board S100 bus Z80 computer here. Um, and it has some issues, I have to say. I've been working around them fairly successfully to get this thing up and doing what I want it to do, but it's a very roundabout way to have to do it. Um, One issue is I can't seem to get the floppy drive controller to work. That's I don't know what's up with that. It seems to be working. I seem to be getting the correct signals, but it's not reading from floppy drives. It's not even reading from floppy drive emulators. So that's one problem. Okay. The main problem I have with this thing, it only has a 2K EEPROM in it for a very rudimentary loader program that would load CPM off of a floppy drive. But since I can't get the floppy drive controller to work, that doesn't work. So a while back, I replaced the 2K loader EEPROM in here with a custom-made monitor that I wrote that allows me to at least bring the system up and do a few things with it. And that made it a whole lot more useful. The main thing that's very useful about that monitor is it allows me to load Intel hex files over the serial port. So I could import things like BASIC into the system and run it out of RAM in there. So I actually had a system that I could boot up and run BASIC on, although I had to go through the intermediate step of loading BASIC through the serial port. Not all that onerous, but still, I'd like to have an instant on system where you flip the switch and it's ready to go. So anyway, my work with the Naboo, if you've seen my work on the Naboo, and I'll put a link to the playlist on the Naboo in the upper right if you want to check that out. I have set up a bank switching system in it for its EEPROM memory, and I can get up to 4 times as much memory, EEPROM memory, into the Naboo as it can handle natively. And I can put stuff in EEPROM and have it there instantly when I want it, like BASIC. So I got to thinking, maybe I could do something similar with this. I could do some bank switching, a whole bunch of 2K banks, and get whatever I wanted that way. But then I had a thought, wait a minute. Maybe I can do something even simpler. The Systemaster has a couple of parallel ports here. What if I designed a board like this one right here? It's all prototyped out, and it's a real spaghetti mess of wiring. But this is what I designed and built. I've got a 28C256 EEPROM in here, so that's 32K by 8 of EEPROM. And I just have 2 latches. And what I came up with, and I'll show you the schematic for this and talk about the logic behind it, how it works in this video, but I'll just show you the board first and talk about it a little bit. So yes, I came up with something that I think is fiendishly simple, and it's a 3-chip solution that allows me to get, 32K of EEPROM in here that I can read into RAM in the Systemaster. And like I said, fiendishly simple. I've got 2 parallel ports on the Systemaster. They're built in, port A and port B. So what I do is I've got port A, all 8 lines of port A come out. And we're using it to output the upper and lower 8 bits of the address for an EEPROM. We actually only need 15, but we're outputting 16. I could expand. I could put a second chip in here if I wanted to. And have a full 64K by 8 of EEPROM in here. But so we're putting out, first we'll put out the 8 low order address lines on port A, and on port B we'll use one of its lines to signal to latch that into the low order address latch. Okay, and then we'll put out the high order address lines on port A, and we'll use another line on port B to tell the latch here to latch the high order address. All right. Now we've got low and high order addresses going into the EEPROM. Next thing we need to do is we need to turn port A from an output to an input, and then use another line on port B to tell the EEPROM, hey, go ahead, output your data. Twiddle the output enable line on the EEPROM. So now we've got the EEPROM data going into port A. And then we use the fourth bit, or actually bit 3 since the numbering starts at 0, to pulse the ready line on port A and tell it that the data is valid. And that will get latched into the Z80 PIO chip there. And then, we can take that data and we can put it in memory, in RAM memory on the Systemaster. So this is how I can read a whole bunch of memory into the Systemaster, into its RAM, and then start executing programs from it. And surprisingly, it works. It worked almost immediately. I just had a little bit of an issue I had to sort out with all this spaghetti wiring, and it worked. So what have I got in the EEPROM? Right now, just basic. That's it. But I have plans for more, and we'll talk about those plans for more here in a little bit. So I've still got my 2K monitor over here. There was a little bit of room left. The monitor didn't take up quite 2K. So there was a little bit of room left at the end of it that I could write a routine that would read all of the data in from this EEPROM and store it in the RAM of the Systemaster so that the programs in the EEPROM are available to run from the Systemaster. Like I said, I've only got BASIC in there right now, but it works, and there's potential for a lot of other stuff. So let me fire this up, and I'll show you how it works. So I'll zoom out here, and I'll turn it on, hopefully. So I'll zoom out here. Let me turn on my oscilloscope. I have the oscilloscope reading the low-level address latch line on the board in there. Like I said, I had to do a little troubleshooting. So I'll try and get rid of some reflections here. That didn't really work too good, did it? I guess we're going to have to live with some reflections because moving my lights doesn't seem to make them go away. Anyway, let me zoom in on the oscilloscope a little bit and focus a little better. And when I turn on the computer, there, we are reading the data out of the EEPROM and into RAM memory on the Systemaster. And if I turn the camera around so that you can see the monitor screen behind me, where we're running a terminal talking to the Systemaster, you can see what just happened. Well, basically what just happened was the computer just booted up and it put out the command menu for my monitor. And you can see up here the version is experimental because this is a lot of rewriting has gone into this to get this to work. I had problems with looping in the beginning where it would just wind up in a boot loop, continually reloading the stuff out of the EEPROM. So I finally solved that problem. Also, I did some other stuff. We could talk about the code a little bit here too. Some of you will be interested in that, I'm sure. I also decided, well, while I'm writing the contents of the EEPROM into RAM, I might as well write the contents of the 2K EEPROM into RAM as well, and then just shut down EEPROM access entirely and run the system entirely out of RAM, which is what we're doing now. So this is a 100% RAM system, and there's a reason I wanted to do that for the future, okay? I would like to get CPM on this machine, and for that, we're going to have to be a 100% RAM system. So I have to get used to the idea of getting my monitor and everything else into RAM and then shutting down the EEPROM. So we've got a 100% RAM system all the way from 0 up to 64K. So, okay, so here's my monitor. So it's a 2K monitor. So normally above 7 FF hex, there's nothing. Just random stuff in memory. But let's do something here. Let's do a dump memory at, say, 2000 hex. What do we got there? Oh, there's stuff there. Oh, look, it's basic. There's basic. It comes up with basic in RAM now. Isn't that nice? And what happens if I push the B button? Let's see. Oh, cold or warm. Well, let's do a cold start. Memory top. Look at that. Z80 basic. Yep. All right. So we've got basic immediately on startup now. It only took a few seconds, like you saw, to load that. I basically overwrite the lower 16K of RAM with contents of half of that EEPROM. I can change that so that I overwrite the whole lower 32K if I want to, but right now I'm overwriting the lower 16K of RAM with the contents of the EEPROM. We're getting basic in there, which takes up 8K of that space. We've got my monitor in there, which takes up the lower 2K of space, and it all just works. It works. It's just instant on. In fact, let me reset the machine and show you the boot up here. And there it is. It took maybe 2 seconds to copy out the contents of the EEPROM, maybe not even that long, copy out the contents of the onboard ROM, and then we're up and running. And it's working perfectly. Now, I say it's working perfectly. That doesn't mean there's not room for improvement. In fact, the next logical steps, I think, would be to combine my 2K EEPROM. Let me go back to the machine here. I think the next logical steps here would be to combine my 2K monitor with basic and anything else I wanted to put in the EEPROM up here, and then just write a simple loader program that all it does on boot up is, just a simple few lines of assembly code. All it does on boot up is load the contents of this EEPROM into the RAM on the Systemaster, shut down the EEPROM access, and then run from RAM. So that's basically the way this thing was designed to work, except with a floppy drive, which I can't seem to get the floppy drive working. And I've tried all kinds of things. Maybe if I replace the floppy drive controller chip, it might work. I don't know. I'll play around with that again in the future. But I'm having a lot of fun getting software into the machine. I'm no longer limited to only 2K. I've got 32K here, and I could potentially do a whole lot more. I could actually use this as kind of like a RAM disk, and I'll write a little software for that. Maybe that's a possibility. So the next logical step, I think, is integrating my 2K monitor into here. In fact, I could add a lot more functions to the monitor because I'm not limited to 2K anymore. The lower 8K of this chip is not being used, so my monitor could grow a lot. We could get a lot of new functions in it. So integrate that into there, along with basic, along with maybe some other stuff I want to put in there. And then once that's all working, get my loader program written. And once all that's working, the next logical step after that would be to get away from the breadboard and do something a little more permanent that can plug into one of the S-100 card slots in there. And for that, well, pardon my messy workbench, but I've got some S-100 prototyping boards over here. So I think this would be perfect application for that. I mean, there's only 3 chips. There's only 3 chips on there. I mean, to make this work as a standalone board without having to use the Systemaster's parallel ports, it's going to take a couple extra chips, but only a couple extra. So we're talking maybe use up a third of this board to do that. And there'll be plenty of space for other things on this board. So that would be the next logical step, to get the hardware something more permanent, where I don't have to worry about just brushing against a wire and then spending an hour trying to debug what came loose and's not working anymore. So yeah, that would be good to get this into something permanent. Okay, and then I can, like I said, there'll be lots of space for other things. So I've been working on some other stuff for the Nabu that might make it into this too. But I think we'll talk about that in another video, okay? Because that's still all theoretical vaporware. Once I actually have something working, we'll talk about it, okay? But let's take a quick look at the schematic for this and talk a little bit about the code that makes it work. All right, let me minimize this, and we'll bring up the KiCad schematic of the system. Like I said, it's just a 3-chip system there in the hardware. Down here we have the interface to the Systemaster. There's basically two I/O headers on the edge of the Systemaster card for the parallel ports. I just sort of combine them into one header here in KiCad just to keep things a little simpler. But we've got port A 0 through 7, and we got port B 0 through 7. And we also need the A strobe pin, also plus 5 volts and ground. So we're getting those all from the Systemaster to power everything else here. The heart of this is the 28C256 EEPROM up here that can hold 32K by 8 of data. At the moment, I've only got basic in it, which takes up about 8K. So only using it to about 1/4 of its capacity, but I think I said in the future I plan on using some more. Certainly I will put my 2K monitor in there, and that 2K monitor may grow in size because now it can grow in size. So how does this all work? Well, we've got the port A lines and the port B lines coming from the Systemaster, and what we do is we set port A to be an output port to start with, and we output lower 8 address bits on port A, which are sent over here to this 74LS573 latch. And then we will make port B bit 0 low, which is connected to the latch. And that will load and latch the data in here. And it will come out here on this side of the chip on the Q lines. And these are connected to the lower address bits, the 8 lower address bits on the EEPROM over here. So now we've got the lower address bits latched. We will put the upper address 8 bits, well actually we only need 7 bits on the port A line. Then we will lower PB1, and that will latch the upper address bits into this other 74LS573. And of course, its outputs are connected to the address inputs of the EEPROM, the upper address inputs. Come back over here to the EEPROM. We have write enable permanently tied to plus 5 volts because we're not going to be writing to it. We have chip select permanently tied to ground, which we need this chip to be selected all the time. So now we have the addresses coming in. We just need an output enable signal, and it will put whatever's data is at the address we're supplying it here on its data output lines here. Well, to do that, first we have to switch port A to be an input port. So we'll do that. The software does that. First switches it to input because you don't want to have this as an output and your EEPROM as an output, or they could fight each other over the bus. We don't want that. So we'll switch the port A to be an input. Then we will lower PB2 down here, which is connected to the output enable of the EEPROM. So when that goes low, now we are putting the data, whatever data is at the address we've selected in the EEPROM is out here on its data bus, and it's going into the port A lines. And we just need to do one more thing to read that data. The Systemaster uses a Z80 PIO chip, and you actually have to put a signal, an A strobe signal, into it to tell it to latch the data coming in on the A lines. So PB3 is connected to the A strobe line, and we just lower PB3 to create a strobe signal, and the data on port A bus is now latched into the Z80 PIO and is available for the processor to read and place into memory where we want it. And then what we do is we basically put all the port B lines back to 1s, and we can start the cycle all over again. We've already put port A into output mode again, so we can just put the next low order address line on it and start the whole sequence of lowering PB0, PB1, PB2, PB3 all over again. So it's very simple and it's fairly quick. You probably didn't see the frequency readout on my oscilloscope while the data was being read out of the EEPROM, but it's about 12.8 kilohertz. So that means about 12.8 thousand times per second we're reading a byte out of this EEPROM. that since we're only reading 16K bytes, it takes less than 2 seconds to read out the entire 16K bytes into the Systemaster RAM. So that is pretty darn quick. Certainly a lot faster than floppy disk access. So I'm pretty happy with the speed at which this is reading out the data. Okay, let's take a quick look at the software that allows this to happen. Okay, let's take a quick look at the code. And there's a fair amount of new code that I've added to the monitor I've written for the Systemaster to implement this external ROM storage scheme of mine. In fact, I've had to make some major changes to get this to work, because I think I mentioned earlier that I wound up in a boot loop in the beginning. So to escape that, I've had to implement a cold and a warm boot scheme here. So when the machine is first turned on, or if you press the reset button, you're going to wind up doing a cold boot. But if you just restart from 0 in the running code in RAM, that's going to be considered a warm boot. And we'll go over how I did that first, and then we'll look at the other stuff. So when the code first executes, first time on system startup or reset, this is, we got all the equates up here, and we got some definitions down here and some jumps, and we're going to get down here. The first code we're actually going to execute here is to initialize a stack. We need to have the stack working so we can call subroutines, okay? So we're going to do that. Then we're going to reach a jump to cold boot. And what's going to happen here is we're just going to jump over the jump to warm boot and come down here to cold boot, okay? And we're going to move on from there. But what's going to happen later on in the process during cold boot is we're going to overwrite the 3 bytes of this jump right here with no ops, so that when we do a warm boot in the future, we're going to come down here and we're just going to just slide right through this, because we're just going to go through those 3 no ops. There won't be a jump here anymore, and we'll come down here to warm boot. And warm boot will jump over all of this cold boot stuff down here to warm boot. Okay, so that's how we avoid being in a boot loop. We avoid doing all this stuff in here over and over and over again, which was what was my problem. So that works. It's a trick I've used on the Nabu in the past with my monitor there, and it worked good. So what happens when we do a cold boot? When we do a cold boot, we're going to, like I say, jump over the warm boot. We're going to come down here to cold boot. And what we're going to do is we're going to turn the RAM on. Basically, when the system comes up first, it's just accessing the ROM. The RAM is shut off, okay? So you've just got that 2K of monitor ROM in low memory that's active, all right? So what we're going to do is we're going to write a value out to the control register, which I'm calling RAM ROM on, and that's defined up here somewhere. There it is. RAM ROM on is 40H. Okay? So we're going to send that out to the control register. So what that's going to do is that's going to turn the RAM on. But it's going to turn it on in such a way that the part of the RAM that shares the address space with the EEPROM in low memory is write only, okay? And of course the EEPROM is read only. So what you can do is you can write into that area of RAM that overlaps the ROM, but you can't read from it. And you can read from that area of ROM that overlaps the RAM, but you can't write to it. So you think, okay, what does this accomplish for us? Well, I'll tell you in a second. Now the rest of the RAM is read-write as it should be. Okay? So what are we going to do next? Next we're going to copy the internal ROM into RAM. So we're going to set up, HL register is going to point to where we want to write to. DE is going to point to where we want to read from. BC is a counter of how many bytes we want to write, and then LDIR will take care of this. HL and DE will be incremented. Every time this loop goes through, BC will be decremented. When it gets to 0, the loop is done. And so what we've done here is we've copied the monitor ROM into RAM in the same area. So the monitor ROM takes up the lower 2K bytes of memory. Well, we've just copied everything on the ROM into RAM in that same 2K bytes of memory. All right. And again, you're asking, well, what does that accomplish? Well, what happens next is we're going to load a value called all RAM into the control register, and all RAM is defined up here as 60H. And what's going to happen is when we send that out to the control register, it's going to turn off ROM access and turn on access, read-write access to the lower portion of RAM. So when we do this, now we're an all-RAM system. We have no ROM in the system now. We are all RAM, but we've copied the monitor ROM into memory so that we can continue executing from it. Just like, you know, we're still in the ROM, although we're in RAM now, and we can overwrite stuff if we want to. So, all right, and I have found if I write to the control register, if you have a Systemaster and you're working on software for it, I know there's rare as hen's teeth. There's probably, you know, the number of people out there working with Systemaster, I could probably count on the fingers of one hand and have a few fingers left over. But if you're doing this, I have found it takes a couple of no-ops after each write to the control register. Otherwise, for some reason, the code goes off into la-la land. So just throw a couple extra no-ops in there every time you write to the control register before you do anything else, and that seems to keep things on track. Okay, so we've done that. We've copied the internal ROM into RAM. Next, we're going to call a program called copy-ROM. And what copy-ROM is going to do is going to copy the external ROM into RAM. In fact, I'll modify this right here just to comment that a little better. So, and we'll talk about copy-ROM here in a minute, but I'm going to finish talking about what goes on during the cold and warm boot, and then we'll go down and look at copy-ROM, okay? So we're going to copy that external ROM into RAM, and then we're going to come back down here, and we're going to go through a procedure I call make warm. And what it's going to do is we're going to load the address of entry, which is way up here above cold boot, into HL. And then we're going to load the memory location that HL points to with 00, or basically a no-op instruction. We're going to increment HL, and we're going to do it again. And we're going to increment HL, and we're going to do it again. And what that does is that overwrites this jump, because now remember, we're operating out of RAM. So we can overwrite stuff in RAM. So that's going to overwrite this jump right here with no ops. So this jump is not going to exist anymore. If we restart from 0, we're going to come down here and we're not going to do this jump anymore. We're just going to slide right through it down to warm boot. And then warm boot will jump over all of this stuff. We don't need to do it again. And come down here, and then we will continue initializing the system, printing startup messages, yada, 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 like we would do during a normal startup. So that's how that all works, okay? So I hope that's understandable. If you have questions, hey, leave a comment. I'll try to answer your questions. But this is how we avoid getting into a boot loop, and by doing a warm and a cold boot, having those two options. Now, I told you I'd talk about copy-ROM and the code that copies the data out of that big EEPROM over there into RAM. So let's go take a look at that. I had just a little bit of space left in the EEPROM. So there was just enough space. I mean, I've got like 6 or 8 bytes left in that 2K now after adding this. I just tacked it on at the end. I mean, I could have put it anywhere, but I just tacked it on to the end of the code here. So here's copy-ROM. It calls copy-ROM. And copy-ROM, first thing it does is it calls setup. And what we need to do here is we need to ensure that both ports are in output mode and port B is outputting all ones. That has to be set up that way, first off, or we're liable to have conflicts. So first thing we're going to do is load A the A register with FF, which is all ones basically, and we're going to output that to the port B's data register. Even before we do anything else to port B, even before you set it up as an output port, you can preload the output, whatever you want to be output in it, you can preload it into the data port. So as soon as you set it up as an output port, that's what will be there. So that's what we're going to do. Up until you set it up and tell the PIO chip what you want it to do, on reset it comes up with high Z on all of its outputs. So they're basically undefined at this point, but they don't conflict with anything either. So we're going to preload FF into PIO B's data latch. We're going to load PIO output, which is something I define up here somewhere. PIO output. There is a number you can send to the control register on the PIO, either control register, there's two of them, that will turn that port into an output port. There's another number, PIO input, which you can send to the control register on that PIO port and make it an input port. So I've defined those two values up here so I don't have to remember them. I just put PIO output or PIO input depending on what I want the ports to be. So if we come back down here, we're going to load A with PIO output, and we're going to set PIO B's control register to be an output port, and we're going to set PIO A's register to be an output port. What's on PIO A at this point really isn't important, okay? It's probably all ones, but it's really undefined, but it's not important what's on PIO A at this point, but it's very important what's on PIO B. It has to be all ones to keep everything copacetic there, so we don't have any kind of data bus conflicts. Okay, so that's setup. So after we've done setup, we're going to load some registers with, just like we did up above to copy out the internal ROM. We're going to do pretty much the same thing. We're going to load HL with our location in memory where we want the data to go. We're going to load DE with our location in external ROM where we're going to start reading from. We're going to load BC with the number of bytes we want to transfer. And then we're going to call get ROM data. Okay? And where's get ROM data? It's way down here at the bottom. So this is read up to 64K bytes of ROM data and store it in RAM pointed to by HL, number of bytes to transfer in BC, address in ROM in DE. We just went over that. So, get ROM data, it's going to call low address latch, which is up here. So we're going to load the address in E because we have, the ROM address is in DE in the DE registers, which is 16-bit register, but E is the lower 8 bits of that register, so we're going to load that into A. We're going to output that on PIO A's data bus, okay? So now we've got the low 8 bits of the address in ROM on the data on PIO A, and we're going to load A with FE, basically all ones except for the 0 bit, and we're going to output that to PIO B data. And what that's going to do is that's going to raise the 0 line, the 0 bit line on PIO B, and that will latch the low address into the low address latch. All right. So we've done that. Then we're going to come down here. The next thing we're going to call is high address latch, and it basically does the same thing. We're going to load the D register, which is the high half of the 16-bit DE register, and we are going to output that on PIO A, and we're going to load FC into A register, into A, and we're going to output that to the PIO B. And what that's going to do is that's going to lower PIO bit 1, just like we lowered PIO bit 0 up here. So that's going to latch the high order address into the high order address latch. All right, so now we've got both halves of the address latched, all 15 bits latched. We're not using the high order bit on the high address yet. Maybe in the future we will. So next we're going to call read ROM byte. So what does this do? Well, this looks pretty complicated, but it's really pretty simple and linear. What happens is we're going to first off load the A register with the PIO input value, and we're going to output that to port A's control register. We're going to set port A to be an input port. We have to do that before we do anything else. Otherwise, we're liable to have a conflict. Next, we're going to load A with F8, and we're going to output that to port B's data port. And what that's going to do is that's going to lower the output 2 line on port B, and that is connected to the, well, that's wrong, that should be OE. So that's connected to the OE line on the EEPROM. So that's going to allow the EEPROM to output the data that's been latched into the address registers onto its data bus. Okay, and its data bus is connected to port A. So port A is now an input. But we need to do one other thing to get the data into port A. So next we're going to load F0 into the A register, and we're going to output that to PIOB's data port. And what we're going to do is we're going to lower the bit 3 line on port B. And that is connected back to port A's strobe line. So we're going to lower the strobe signal. And that's going to tell the PIO chip on the Systemaster that there's data on the A port that it needs to latch into its input register. Next, we're going to put F8 back on the PIOB. Basically, we're going to raise the bit 3 line back up to end the strobe signal. Next, we're going to read the data from PIO-A into the accumulator because we just latched it in with the strobe signal. Then we're going to write that data in A out to the memory location referenced by HL here. Next, we're going to load A with FF, and we're going to output that to PIO port B. We're going to raise all the lines on PIO port B back to 1, and we're going to load A with PIO output, and we're going to reset port A's control register to be an output port. We're basically back in the same state we were at the beginning of get ROM data, with all 1s on PIOB and PIO-A as an output port. Alright, so down here we're going to, if we come back from read ROM byte, we're going to increment HL, increment DE, decrement BC, and then we're going to check and see if BC is 0. And there's no really straightforward way to see if one of the 16-bit registers is at 0 or not. Decrementing it, if you reach 0, it doesn't affect the 0 flag if you cross 0 while you're decrementing a 16-bit register. So you have to go through a little bit of gymnastics to figure out whether you have decremented BC all the way down to 0. So first you load the accumulator with the contents of the C register, and then you OR it with the contents of the B register. And if you've reached 0, the result of this calculation will be 0, and it will trip the 0 flag. So then you can check. You can compare. Jump relative, if not 0, back up here and keep going, and keep going, and keep going until this is 0. And then you don't jump again, and then you return. So that's how that all works. Sounds complicated. It's actually pretty simple, and it's amazingly quick. Amazingly quick. Less than 2 seconds to copy all that ROM data into RAM. You know, once we hit this copy ROM process up here. So that's how that works. I hope I explained that. But yeah, leave questions if you don't understand it. Back in the past, I published this code because 1 or 2 people wanted it. There are a couple people out there working with Systemasters. So I published a copy of this monitor I created for the Systemaster. So of those handful of people, there's probably very few that are going to implement this external ROM modification, I'm thinking. But if there is, you know, a lot of demand for it, I will publish this code here. So let me know in the comments if there's anybody out there who wants this code. All right? Otherwise, I'm probably not going to bother publishing it, or you can probably do your own modifications based on careful watching of this video and taking some notes. I guess if you're still watching, you must have found this fairly interesting, and if so, I'd like to say thanks for watching, and watch for future updates on this project as I get it built onto that proto board in a more permanent manner and put down into one of the slots on the Systemaster here. There'll have to be some changes made in the software and the hardware to get this to work on a separate card and free up the PIO ports over here. But I think that's fairly simple and straightforward. So I'm going to get to work on that, and so watch for a future update on this. And I may actually up the capacity of the EEPROM to something a little bigger. Possibility. You know what? I could just keep latching addresses into address latches and come up with as much storage space as I could possibly desire. And like I said, maybe even turn this into kind of like a ROM drive. So that's a possibility too down the road. And also, there's going to be some other changes made on this based on some work I'm doing with the Nabu and with my Jazz 80 breadboard computer. And some of the work I'm doing here is going to wind up in them. There's a lot of cross-pollination going on between these three projects. So check those out. And thanks again for watching this video. If you found it all interesting, educational, informative, inspirational, whatever, give it a like, give it a thumbs up, and I'll see you in the next video. Bye.